Sir, good morning, sir. Good morning, sir.
Very good morning. Can you hear me?
Yes, sir, I can hear you. Yeah, just now, like a student came to lab, sir.
No worries.
So they will be joining in another 5 minutes, sir.
There also was a problem with the headphone. I hope you guys can hear me clearly now.
Okay. Yes, sir. Yes, your voice is clear, sir.
Okay.
Yeah, yeah, sir. So just give me 2 minutes. Others will join, and I'll let you know, sir.
Sure.
Yeah, thank you.
Hi Vishnu, how are you?
Good morning, sir. Fine, sir. So, how about you, sir?
I'm good, thank you. I hope things are okay. You're not there for a week.
Yes, sir. For the previous week, sir.
Fine.
Sir, hello, sir.
Yes, Professor.
So comparatively, today we'll have less strength, sir, because they have some NPTL exam, sir.
Okay.
So like, yeah, comparatively, there will be some less strength. So whoever is available in the college, they will be joining, sir.
Okay.
Yeah, yes, sir. Just 2 minutes, sir. Like they are, some other students are also joining the session.
Sure.
Yeah, yeah.
I'll wait
Thank you.
for your signal to start the session.
Yeah, yeah, please, sir. Thank you so much, sir.
Okay. So Vishnu, you were able to submit all projects, Vishnu and others.
Sir, actually, we didn't submit the last week project, sir,
Okay.
due to this NPTL exam, sir. We can submit it by tomorrow or by this week, by next week, Thursday, sir. Both projects we can submit, sir.
Okay. No problem.
Actually, I have mailed you to regarding this issue, sir.
Oh, when?
I think yesterday, sir.
Okay. I haven't checked my mail. I'll respond.
Okay, sir. Because we have a mandatory open elective exam, sir, this week.
Sure. I will extend the date for the last project as well as this project till end of this week. Okay. End
Okay,
of
sir. Thank
coming
you, sir.
week.
Thank you, sir.
Okay. Also, I mentioned in last week's session that Professor Suresh and myself will try to conclude on how many more topics and sessions, uh, and also about the date for the final certificate issue, which would be most likely in person, in campus event. We'll finalize and come back to you guys, but we couldn't conclude yet, and I'm hoping, probably by mid next week, coming week, or by end of next week, we would have that clarity that I'd like to achieve with Suresh, Professor Suresh, and I'll share with you guys as I conclude with Professor Suresh.
I'll make a note of it, sir.
Sure. So how is the first semester progress of the students in terms of the grades, Professor Suresh, CSM, and both the computer departments? Is it better than last year?
Sir, if you don't mind, could you please repeat the question, sir? I didn't get
The
you.
grades, the performance of students in this internals comparative to last year across all both the computer science departments, is it better, improved, or is it
Yes, sir.
tough this
They're
time?
doing better. They're doing better, sir.
Okay, it's good to know.
In fact, students are working down multiple things, so we can find a gradual increase in their improvement, sir.
That's nice.
Yeah, sir.
So by the time these kids come out of the college in next 2 to 4 semesters, entire world would be reverberating only with the generative AI and nothing else.
Correct, sir. Correct.
So unless they are prepared for it mentally, physically, knowledgeably, it is going to be real tough for all the students across the globe, particularly in countries like India, US, most developed and developing nations. The jobs are going to be only in the artificial intelligence, which are high paying jobs. Generative AI, not even AI, in the next 2 to 4 years. So I hope students will keep this in their mind and build and execute their learning plan accordingly, so that you know they not only make themselves happy and joyous when they get a good job, a high paying job, they also make their teachers, their institutions, most importantly their parents and family, more joyous than themselves. I would like them to understand that.
Yes, sir. I guess like when you come for this offline session,
Right.
definitely I guess you can give some awareness on this, and I hope they can find it useful, sir.
Right. Definitely.
Yes. Sir, I guess we can start this session, sir.
Excellent.
Yes.
So, good morning, everyone. I hope you guys are as charged up as you were at the beginning of the semester. So, today's session is quite interesting and quite revolutionary. The concepts that form the basis for today's topic of machine learning algorithm, which is naive Bayes algorithm. Anyone knows the meaning of naive? I have circled or put a square or rectangle here. Anyone knows the meaning, English meaning of this term naive? Naive, naivete. These are mostly French slash, Latin words. Anyone knows?
Some maybe innocent.
Something similar. Uh, not being smart, being believing what one sees, right? Innocence. So some sort of innocence is part of this model that builds on Bayes theorem. And when we say Bayes theorem, we obviously are talking about probability, which means this algorithm is the central, the fulcrum and the core of this algorithm is probability or probabilistic model that takes some sort of naivete or innocence or assumption to do the inference. That is a one-line summary of this model. And where do we use such models? And what is the benefit of such models? And how do they distinguish from the other models and concepts that we have so far learned? The linear regression, logistic regression, support vector machine, all these classifiers or regressors, right? So we're going to talk about it, and it's very simple yet highly powerful algorithm in classification. Let's take a dive into it. So instead of just focusing on this algorithm, which is fairly straightforward, of course, builds on the probability models, but I spent some time trying to get you real mathematical, not only mathematical, real basic fundamentals of probability, starting with the real life scenario, and then the significance of probability models in machine learning algorithms, essentially driven by statistics. Probability and statistics is a subject that not only you guys, myself, and I studied engineering in 88 and 92. I'm a class of 92 from GPREC. And even 5 to 10 years ahead, 2 decades ahead of me, my seniors also studied statistics and probability. They formed mathematical foundation and the framework for some sort of predictions by companies, by governments, etc. In fact, India has long back, post-independence, started an institute called ISI, Indian Statistical Institute, which is purely, whose focus has been only statistics and probability to aid government in all these metrics and then all these statistics for the economics, Ministry of Economics related to the budgeting, etc. Right? So machine learning algorithm is nothing but leveraging machines and then automating those statistical methods and probability theorem or theories into making more realistic predictions based on a lot of data. Statistics always based its decisions on sampled data. If there are 1 billion people, or for example, when there is an election, people conduct a poll, exit poll, entry poll. So they take a sizable sample, 5%, 10%. And then they, based on the probability and statistics, they correlate. We know the correlation, right? And then they give the results, right? So I'm going to spend some time building those, infusing those and building those fundamentals, walking you through, starting with a real life scenario. And then we take an example, use case of email spam filtering to explain this particular naive based classification algorithm. And then we understand most important key terms of the probabilistic models, particularly prior and posterior probabilities. Remember, they may sound alpha, beta, Greek, but these probability key terms are super important for you because they're going to stay there with you forever if you're building career in machine learning. The Bayes theorem, Bayes rule, Bayesian networks, and then the posterior prior probabilities. They actually form a lot of fundamental computing algorithms in today's 5G and 6G. I've recently done a master's from IIT Kanpur. Use how machine learning algorithms can predict in estimating the signal based on the past data. Something that I talked about to you guys on online learning, incremental online learning based on, the difference between the current coefficients and then the current previous estimate of the coefficients, and then the current inputs signal that has been observed, what is the delta error, etc. So these are powerful concepts that are going to go deep into machine learning. So better focus attention and then ask questions, right? And then we talk about the project details. And there is also something very important that you would come across everywhere. It's also called additive smoothing, which is mathematically known as Laplace smoothing. I'm sure all of you know Laplace transformations, most likely, right? So which is to solve the differential equations, higher order differential equations, which essentially transforms a time domain representation of signal data into frequency domain. So essentially this has relationship with Fourier transforms. Fourier transforms are the fundamental blocks of any digital signal processing, FFTs. IFTs and FFTs they come as a package with chips today. And they are taken it granted. Without that, there is no mobile phone, there is no signal processing, there is no video, there is nothing. Fourier transforms are so super important, right? They are like, addition, subtraction, division, and multiplication. The fundamental operations of mathematics that drive the world today, right? And there are a couple of other topics, other key terms like TF, term frequency and inverse document frequency, which are super important, which are the basic building blocks for something so critical today called word embedding, vectorization. Word embedding or tokenization is a key component of ChatGPTs or generative models. Any model, you take it, Cloud, you take it, ChatGPT, you take Copilot, all of them essentially part of the NLP, right? Natural language processing. You need to tokenize the words, and then you need to build a space to see the relevance of terms, each token, each word, to see what is the meaning, to understand the semantic meaning of the sentence for the prediction. And then we will get into the project demo and we'll go to the Q&A, right? All right. So let's take a practical scenario. So stay with me and don't lose me. And if you have a question, ask me, because this is very, very important. This is for you guys, for your future, right? So let's say you are a doctor and a patient comes to you with a suspicion that he may have a very rare disease, right? And he obviously would like to get it tested. And there are already established tests. Imagine how the world went through the rare disease, not only rare, unknown disease. All of us went through 3 years back, right? COVID. We didn't have any tests back then. and we built those tests in the shortest possible time and vaccines as well. So the doctor also has an accurate test. Also, please remember, accuracy does not mean 100% perfect. It means it gives the accurate results. It may not be perfect. It may still be imperfect, but it gives accurate results. Whatever it says, it means it. Whether it says 90% perfect or 80% perfect, well, those are all, there are other dependent factors, right? The variation in the blood samples or any sample that has been collected, etc. So because of these factors, right, doctor has to make informed decision based on the test result and also based on previous history of that patient and other similar patients. Maybe it's a disease that started because of seasonal disease. So he has to hypothesize based on the test result, which is evidence, right? So let's call it, he's going to say whether the patient does not have the disease or has the disease. That has to be driven by the test result and also based on some prior information, prior belief, historical information, right? Let's say that he knows around 1% of people who have tested have this disease. So probability of the prior information, historical information, is 1% people have the disease, 0.01%, which is a true positive. We know true positive, false positives, all that, right? Let's say from what he has experienced so far, even if it is the test result is positive, 95% of the people who tested positive in the test only actually has the disease. The rest, 5%, were false negatives or the false positives. Actually, it is false positive. And around 1.1% people who have tested so far from his experience, rough numbers, right? Around 1.1% of the total population has been tested, whether tested positive, tested negative, totally. Probably it could be more than 1%. It could be even 10%. I took 1% just for the sake of 1.1% for the sake of proving a point, right? So even if the test result is positive, when we say test result is positive, it means the patient has been tested assuming he has the disease, and then it turned out he has the disease, then the result is called positive. Patient has been tested assuming he has the disease, but the result turns out he does not have the disease, then the result is called negative. So you have to always remember, with respect to medical test reports, even though we always say be positive, feel positive, but not for the medical test report. For medical test report, we want the report to be negative. We want to feel positive to have a negative report. So even though a patient is tested negative, it is or positive. Let's take in this case, whichever you take, because of the other factors, 95% likelihood or accuracy, patient may not truly be negative or positive. So the test result is not perfect. It obviously contains false positives or false positives or false negatives, both ways. Right? So doctor needs to find, obviously, he takes the standard approach all of us will do without knowing and involuntarily. Some sort of guesswork, estimated guess or judicious guess based on the evidence. So he will hypothesize, okay, I got the current test result from the lab test, and I know some information from the past, some prior information of how many people got, what is the percentage, people of his similar profile, right? And he will hypothesize based on some model, some numbers, some formula, what could be the probability considering these factors the patient actually is either truly positive or truly negative, taking into account the evidence, current evidence or current test report result that he got. But how? What is that formula? How does he arrive at that probability? What formula does he or she use? That forms the basis for all the decision making employed by all the machine learning algorithms, the fundamental block called Bayes theorem or Bayesian probability, right? Which essentially you have some belief, right? So far, in the first wave, we all felt COVID first wave, somebody tested positive, it is highly likely that it is fatal, right? Majority percentage of the people who tested positive had gone through fatalities and probably 10 to 20% death as well, right? So there is some prior information, prior belief, and then there is a current test result or current evidence of some event or some hypothesis. And then you would like to arrive at what is the probability of actually the disease existing. That is driven mathematically and scientifically based on this model, which is driven by probability. Probability comes from observation. It's empirical, Bayesian probability, named after the scientist Bayes, right? I think he may be a French scientist. So Bayesian probability, Bayesian rule, Bayes theorem, these are all the various names to the same concept, same formula, same notion, comes to the rescue of the doctor. Any questions so far? This scenario is critically important and is prevalent and ubiquitous across all the scenarios or all the machine learning algorithms, all the use cases. You have some prior beliefs, you have some current evidence, right? And what could be the outcome? It's used heavily in all the exit polls, in all the elections across the globe. The Nielsen guys that conduct the survey, they are the experts in using the Bayesian probability models in arriving at the predictions, survey results, etc., or correlating survey results to the entire population. So such machine learning model or such model to predict or to infer is called and is based on probability, hence it is called, or hence such models are called probabilistic models. And the inference that you make out of such models is a probabilistic inference. Whereas if you recall linear regression, logistic regression, they were purely driven by mathematical formulas, linear equation or sigmoid function. These are all mathematical formulas that have specific values. Whereas these models, probability models, are driven by a frequent test approach of the past data, and then how aberrant the current, based on the current evidence and the certain characteristics of this particular sample, how would it deviate? What percentage would it deviate from the true results? Is what essentially a probabilistic model helps you arrive at in achieving the inference. So it is deducing or inferring or predicting an unknown or a hidden information, be it a value, be it a classification label, from the known data, historical data, and also evidence, the current evidence, and then the probability theory, which is the Bayes theory, right? So this obviously involves calculating the probabilities and updating the probabilities. Updating why? Every time a new patient comes in, you take the previous data till the last patient and the current evidence. So continually your prior information is improving, right? Your prior knowledge, prior belief is improving. So it's just like trial and error method. And remembering what happened last time, just like without knowing, you put somebody offered you, somebody has a question. Soumya, you have a question? I see your hand raised. I believe it is a mistake. Okay. Somebody served you the coffee and without thinking much, you just had a sip and then you realized it's a hot piping hot coffee, so hot that you burnt temporarily your upper surface of the tongue, right? And then you're not going to have the sip immediately because you learned. You learn from the experience and you wait for some time, or you cool it off a little bit and then take it a little later. You're learning, right? So it is a sort of same model when every patient comes in and then your data improves in terms of your prior knowledge, and you take that into account and you start computing the probabilistic or probability of the current evidence being true based on the past or prior information. So they are in terms of so essentially probability models also use not to deriving the probabilities, what is known as a probability distributions, some distributions. These distributions, yes, Shiva Charita Reddy, your hand is up. Do you have any question? Okay. They also take from hundreds of years of our ancestors' effort in being inquisitive, being dedicating their lives in observing data pattern. They have codified their observations, their learning, particularly mathematicians, their observance of some pattern of data in the form of data patterns. One very well-known pattern that we know, that many of the the data patterns in real life, be it diseases or be it performance of people, be it completion of a project, most of the times they follow what is something known as a bell curve normal distribution or a standard normal distribution. These are not developed overnight, nor God appeared to Euler or Mr. Gaussian and told him, hey, look, this particular thing follows a pattern like a bell curve. These are observed based on, these are derived based on the data, their life's work across many scientists, of many scientists. So many scientists have arrived at such, deduced and created or invented such models in probability. And those probability distributions for particular scenarios in real life is what would be used in machine learning probabilistic inference models. Some of them you already must have known them, not specifically, but you must have heard these names, hidden Markov model, Markov random fields. All these are, HMM is used in, GMM and HMM are used heavily, Gaussian mixer model. They're used heavily in speech processing, speech recognition. Siri that you use every day, or the Google speech recognizer, right? Google Voice, Alexas of the world. They all use GMMs and HMMs, nothing else, in recognizing essentially the patterns and then responding based on those patterns, right? So essentially, inference is about computing an unknown probability or computing the probability of a value and its expectation. Again, expectation is a mathematical term as well. Maximum likelihood, expectation, inference, these are the terms that are fundamental terms in machine learning algorithms. Right? Expectation or computing the probability given some observed data. Right? So we have seen models till today, linear regression, logistic regression, then the support vector machines. And we've never talked about any probability there. And we've never talked about any distributions there, right, of the data. So all those models that we've spoken so far, other than today's model, they are, if you look at, they are predicting, if you take the logistic regression, a binary classification, based on input X, that could be a simple scalar or a vector, multiple features. We take this value and we run some mathematical logistic or linear regression. Essentially, we regress, whether they are continuous values or categorical values. And we translate that into some sort of sigmoid, if it is a classification, or we translate that into some sort of continuous value for the, continuous value for the non-classification values, predictions, right? So the key here always is, if you just translate that into mathematics, we always predicted a value y. Let's not take probability. We predicted y given input x, and x can be a scalar or vector. The y can be again a categorical value or a continuous value. So we always, it's like a linear model, right? Like a feed forward neural network. You got some x and you have some mathematical model, mental model, and you predicted y. Straightforward. And in case of discrimination or classification, it's called you're discriminating the output, whether it belongs to one of the two classes or one of the multiple classes, binary or multinomial classification. Hence, it is a discriminative model. You have an input, you run mathematical model, and either you predict a value or you predict the output to belonging to a particular, you discriminate the the input belonging to a particular output, known classes. That's a discriminative model. Whereas in case of generative models, which form the basis for today's generative AI, generative models, there could be hundreds of models, right? You predict, your equation is, you predict a probability of I given y, right? Given y, what would be my x? So it's the reverse. It's like back propagation. This is during the training. I know the output is this. Given this y, what could be the x? What could be the input? That means, let's take a visual box. Let's say this is the box. You know the output, but you don't know the x. During the training, you want to guess. It's also called some sort of finding the masked word in the generative AI or the neural network. You know the output, you want to guess what is the input. How would you guess? You need some reference. And that is where comes your data model, whether this model, that model, and that data model is the probability distribution of such data set for which you are applying. So essentially, you try to, during your training, you build a model or a mathematical model, trying to guess what could be the input when you know the output based on certain probabilistic model, either one or two combinations you take as a reference based on the empirical studies so far in that field. And that model is a generative model. Essentially, that is what is used by all generative AI today to generate something. Next to generate an image, to generate a speech, to generate a video, everything, right? So you are modeling the probability. Essentially, you're modeling for this Y, what are the various combinations of input vector, and that is nothing but your table, right? It could be million, billion combinations, right? If it is a higher dimensional vector input or multiple, many features, it's a permutations and combinations. If input has n features, how many combinations are possible? N factorial, right? N factorial is, I don't have to tell you that can, if n is 20 or 100 or 1000 dimensions, you can imagine it goes into, I don't know, hexa, peta, whatever combinations, right? So essentially, it's kind of creating such table. It's like your number tables that we learned 1 to 20 that we have learned for multiplication. So in a nutshell, discriminative models, they model a conditional probability. Given the input X, what is the output? It is conditional probability. And generative models, they model the joint probability. Current output is Y and current input is X. So what is the probability these two can occur jointly in million combinations that I am observing the training? So they model, the generative models model the joint probability. Discriminative models model the conditional probability. Given the input, what is the probability or what is the value of output? So here, in discrimination, boundary is learned, decision boundary. Whereas in the generative models, we will learn the data distribution based on the training, the data distribution of this black box. Of course, advantages. In discrimination, you're only classifying, you're not generating anything. You can creating a value, you are identifying a value, or you are classifying a given input belonging to a particular class. Whereas in generative models, you can generate the data because you have the data distribution, and if you can always take any value here randomly, and then that value in the Y is this. You can always say this is the output. You can generate Y. And that is what is used today in training the neural networks. And this process is called synthesizing the data. And so generated data is called synthetic data. Many of the industry deployed machine learning algorithms do use synthetic generation of the data because you don't get the data that easily. You think that data availability is that easy, but the real data, it's not that easy to get. So you can generate data in generative models. Where is my, generative models. That's not possible in discriminative model. Obviously, classification, regression are the use cases for the discriminative models. Data density estimation, data generation are the use cases for the generative models. Any questions so far? With that being said, let's look at the fundamental Bayes theorem of the conditional probabilities, or dependence and independence concepts that are associated with the probabilities and the associated distribution, right? So essentially Bayes' theorem, it involves the inference or predicting a class or a value based on two or more events or data points. For us, each data point is an event. If there are, we'll have thousands or millions of data points or events. Based on that, we need to classify whether a particular outcome is going to belong to a class or what is its value. So when your outcome is going to be dependent on more than one inputs or events, you would need to estimate the joint probability of some outcome occurring given multiple events. If you, let's restrict our discussion to only two events of A and B, then a joint probability of both these events occurring together is, if you consider that as a Y, in probability domain realm, it is written as probability of A intersection B. A intersection B given Y, because Y is the output. And this intersection comes from, probability theory is based on sets, right? So this is essentially from the set theorem, the common area between domain A or set A and set B, right? If you take, here is the example, right? This is the A intersection B or X intersection Y. These are two sets, and they have a common intersected area, right? So from the joint probability theorem, which is the fundamental first principles of probability, if there are two events and their intersection or their joint probability is represented by, if A and B are independent events, right, is represented by the multiplication of event A, probability of A occurring and probability of B occurring, because they both are independent. It's like if somebody asks you what could be the best example of a joint probability, let's say two independent events, let's say tomorrow rain occurring or next week rain occurring, and then election results happening. Probably election results may be stopped even because if it is a severe rain, but any two independent events, right? If they are independent, then their joint probability is a multiplication of their individual probabilities. But if they are dependent, right? For example, if you toss a coin, if it turns out head, we for sure know tail is not going to happen. They're also called mutually exclusive, right? So if occurring one event will have an impact on the other event, for example, let's say there is a cricket match, and then if Virat Kohli is going to make a century, obviously he's going to consume lots of balls if it is a T20, lots of overs he's going to consume, and he would be left with other players would be left with lesser overs, and they may not be able to make a century. So there is a dependence, right? So if two events are, what is the probability that Virat Kohli makes a century, and also who is the next guy? Let's say Nitin Reddy makes the century. Probably Nitin Reddy comes later, and his making century will be dependent on whether Virat Kohli stays long or Virat Kohli makes a century or stays long or gets out faster. If the Virat Kohli gets out faster, Nitin comes later, and then he has got lots of overs, then probably he may make century, Nitin Reddy, right? So these are conditional events. So if there are two conditional events, then the probability of joint probability for dependent or conditional events is probability of but A occurring and probability of B occurring given A has occurred. Also, if B occurs first, probability of B occurring multiplied by probability of A occurring given B has occurred. This is super important, guys. This equation that I have written here is super important in your lives if you're building AI and ML, because Bayes' theorem, whether you like it or not, is going to be there forever if you are in this field. And this is the fundamental equation that I'm going to derive in next one step. Bayes' theorem, Bayes' rule is equals to probability of B multiplied by probability of A given B. Right? Both are same, both have to be same, right? Then you can derive, if you want, you can also do probability of B given probability of A, but generally it is stated probability of A given B is probability of B given A multiplied by probability of A and divided by probability of B. So essentially A is hypothesis. It's just like what doctor is trying to hypothesize. I know the evidence, test result B. And I would like to arrive at what is the probability that the patient actually has the disease, even though the test result evidence says positive, the patient has the disease, is nothing but probability of, B. What is B? Probability of medical test result being true given patient has the disease, which is essentially the accuracy in a way, or the likelihood. And what we know so far, probability of the disease occurring across the population, and the probability of the evidence, again the likelihood in general across the sample. Right? Any questions here, guys? Okay, so let's understand key terms quickly before we jump into the next step or the next part of the naive Bayes, right? So probability, Bayesian probability, Bayes theorem or the rule is nothing but it is used for, it's a rule that talks about conditional probability to infer based on the statistical data which you have chronicled so far and arrived at some sort of probabilities to hypothesize an outcome, right? It's obviously rooted on the Bayes theorem, and it is based on this formula that we just talked about. Probability of any hypothesis given an evidence, which is also called posterior probability, because you're doing it post the evidence and post the prior information, because you already have the prior and you're doing it after prior, this inferencing or inferring, right? So the posterior probability of any outcome, in this case the patient having the disease, is nothing but probability of evidence being true given hypothesis. It's also called evidence likelihood. How likely is that the test result is true, the evidence is true, right? And this obviously is based on observing the evidence E given hypothesis in the past data, because in the past doctor might have predicted based on the evidence patient truly has the disease, but then after observing certain days after the test result and also after medication, giving the therapy or administering the therapeutic cycle, it is found that the patient actually did not have the disease after the second test in next 2-3 days. So you have collected the probability of the efficacy of such evidence. So this is the evidence likelihood, probability of evidence given hypothesis. And these two are known as prior probabilities. One is obviously the probability of hypothesis being true, meaning the patient having disease is true for the population so far, prior probability. How many patients truly had the disease? And the other one is called probability of the medical test result being true, which is observed across multiple user tests, multiple test results, which is summed up across for given test result across all various patients. The likelihood of the evidence, and it's a margin, it's summed up across all such test results, hence it's called marginal probability. The term marginal comes from statistics 50-60 years back, when statistics, I think statistics started around the 40s and 50s, post World War II, as a stream of science across the academia across the globe. It's a process of summing over value of one variable against other variable for all instances. If you plot some value against variable 1, x1 and x2, so summing up x2 across all x1s of interest is marginalization or summing up. So here we are summing up evidence E that the test result is true across all possible hypotheses, across all possible positive results that patient truly had or patient had the disease, right? So intuitively, if you look at, something would happen, had happened in the past, let's take the example of the COVID, right? So in the second wave or third wave, if somebody had, the cold and then those pains and then the fever, without any test result, even a 15-year or 10-year-old could have said, looks like you have you've contracted COVID. So that is the prior belief. Then you go for the test, and the test result comes out. Sensory evidence, likelihood, right? Test result, nothing is absolute and perfect, right? They're only to the level of 99% or something. At the most, 99.99999. 6 nines is what is called 6 sigma. Six sigma comes from the statistics, where your accuracy is 6 nines after the decimal 99. 99.99999, right? So if the test result says, hey, it is highly likely the patient has COVID, but there is still maybe 5-10% probability that the test result may be false, right? And that is where your posterior probability helps based on what you have experienced in the past, prior belief, what the current evidence says, and that would be somewhere in between. That is the intuitive meaning of Bayesian probability or prior, posterior or prior probabilities and the current evidences. This is super important to understand, guys. Not many people understand the intuitive meaning of Bayesian theorem, Bayes' law, and its application, and prior and posterior probabilities and their clear definition. Any questions? All right. So now computing, helping the doctor, since he has the test result, right? He knows the test result accuracy was 95%. And prior patient disease probability in total population was around 1%, so 0.01. And then the prior probability of test results across all populations being positive was 1.1%. So even though test results said patient had disease, it is only 96.4% that the patient may have the disease. Other 25%, which is a sizable percentage, that the patient may not have that disease, rare disease. So though the test result is positive, the patient has only the probability of 86% being infected with the disease because of clinical ethics and mandatory rules and standard operating procedure. The doctor has to start the medication therapy for that disease. So anything beyond 50%, the doctor would start the medication or the therapeutic cycle or therapy for that disease, right? So test results, obviously, that there is a probability that the doctor arrives at in deciding, in inferring whether the patient has the disease or not, and to start the therapeutic or the therapy or therapeutic cycle or not. Any questions? Right. So if you look at here is, again, let's understand intuitively. So this was our prior belief, this is what the evidence is, and this is where we are somewhere in between when we predict. So naturally, this guy moving towards the evidence or the sensory result is where our prediction error is less, right? If you see here. But if our prior beliefs are so drastically far away, then our prediction error also is going to be a lot, highly variant. So ideally, we want all these three should be falling within the same distribution, right? And that is where our accuracy levels, prediction, prior information, and then the current evidence would fall aligned. That is our goal, right? In building the models. Also, to now get into the Bayesian probability and also to get into naive Bayes, so in case if we have multiple events impacting the outcome, obviously we need to look at a joint probability, and joint probability is nothing but the intersection of all the events, all the sets, all the domains of data, sets of domains of data intersecting. This intersection is what the joint probability intersection, right? Even here, this is the joint, right? So to have the joint probability when you have multiple events to predict or infer something, you need to have the joint probability fundamental rule that you need to apply, that probability of event A multiplied by probability of second event given first event, probability of third event given joint probability of first event and second event, blah, 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 till probability of last event occurring given last n-1 events collectively, jointly occurring. And imagine how, if you are looking at thousands of such events or thousands of features, event is a feature, right, or data sample. We're talking about, monstrous computational demand here, right? If n is even 1,000, imagine it's a probability of A2 given 99,909 jointly occurring. That again needs to be derived by So it's going to be like Fibonacci expression, right? Recursive. It's simply is not going to be possible to compute, even using lots of computational power. And particularly if you're looking at, many features, many dimensions, it's gonna get intractable. It's not going to be tractable, right? Intractable. Let's look at an example, real life case where it is intractable. Let's case all of you know you've used Gmails and many of those Hotmails, etc. So they have these days filters, spam filters, right? So each mail contains 1,000 words, 10,000 words sometimes, attachments. So your features are nothing but the content. Each word is a feature, right? And if you consider a maximum, if you take an Oxford English Dictionary, there are not only words and other expressions of acronyms, abbreviations, special characters, commas, all those, symbols of the English grammar, and these days mathematical symbols as well are part of the English dictionary. There are around 6 lakh entries in Oxford English Dictionary. So we may extend this around 12-15, guys. I am sure that it may go another 5-10 minutes past 12:15, but let's try to wrap up quickly. So there are around 6,600,000 words in the entire English dictionary. It would be interesting to know, and if somebody can come back and tell me in the next session, how many Telugu words are there in a Telugu dictionary? So it's a homework for you guys. Somebody come back and tell me in the next session, tomorrow, not next week. How many total, what is the vocabulary size of a Telugu dictionary? Imagine you're going to take up a project to build a Telugu language LLM. Nobody had built that yet, and probably I've not heard anybody building it. You would need that. We would need that, right? LLM, we need a Telugu LLM. People are building Hindi LLMs. Ambani's are building. Mr. Ola is building, founder of Ola, Bhavesh Agarwal. And I think NVIDIA guy was there yesterday or day before with Mr. Ambani, and they're making a big waves of building. We're going to build Indian models. And there is a Krutrim. Krutrim is from these guys, Ola. And then there is one more company called Sarvam. I think IAC professor or some IIT professor started. So it would be good to know what is the vocabulary size of Telugu language, right? So we'll have a vector of, let's say we represent all the words of the dictionary in a vector, which is of size 600,000 dimensions or features, right? So that means if we are talking about a jth word in the dictionary, we are talking about Vj in this vector. And if, let's say, if that word is present in our email, we represent Vj as 1. And if it is not present in our email, Vj as 0. So for each email, we build a feature vector of 600,000 dimensions, 6 lakh dimensions, and each value of that dimension or feature is 1 or 0. If that word is in the dictionary, meaning email contains a word from the dictionary, it's 1. If that word is not there, that position value, that index value is 0. Right? So let's take a received email contains this sentence in a subject or in the body. Enter the Diwali festival, Deepavali festive bash with biggest discounts. Obviously, you get a sense this looks like a spam, right? A promotional mail. Now, let's try to build this vector, input vector V, for this email that contains only this sentence, or that contains this sentence apart from other content. So let's look at enter. So we have to look at each word and what is its position in the dictionary. So that is what I have prepared here. Word enter has a position in the Oxford English Dictionary, Oxford English Dictionary at 32,500 position. Da is at 5,75,000 position. I have taken liberty in, you know, what do you call it? Adjusting the numbers to the nearest thousands, position to the nearest thousand, right? Rounding the position numbers to the nearest thousands for the ease of understanding. So Diwali also is a part of dictionary. You know, when all tikka, chicken tikka is a national dish for United Kingdom. There's no wonder that Diwali is also part of their dictionary, right? Chicken tikka is UK's national dish, by the way, if you guys are aware. I think Tony Blair has declared that as their national dish back in early 2000 or so when he was the prime minister. So these are the indices of these words in the Oxford Dictionary. Let's say the email is a spam, then we call it Y is 1. If it is a genuine, 0. So now let's try to build the vector. So the vector V for this sample email, you know, it may contain all other from position 1. We know this is 6 lakhs because it has to represent all the words in the dictionary. And with respect to dictionary, the first word, second word, we have enter. We're ignoring all other content. So 32,500 would have the value 1. And the previous one, immediately next one, 0, because that content is not there in the email. As I said, it contains only this sentence, right? All others are 0. In the same way, bash is 37,500, so that contains 1. Biggest is 47,500. That's value. That position is represented as 1 in this vector. Blah 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 till 6 lakh word, which is 0. The last one that we have as per our sample is width. Width has this position number, hence that value in that position in this vector would be 1. Questions? Now, so if we have to compute the joint probability as we have seen earlier, this is going to be intractable because we are going to have a joint probability of 6 lakh independent events occurring conditionally, because these words can happen. Enter, bash, biggest, discounts can happen not only in this mail with these words, but also with other words, right? If you take discounts, when will it happen? It can happen alongside, you know, when an email comes with from first word, whichever is the first word in the dictionary, maybe it's a dot or number 1 to Z. How many words are there as per our count I told you? So it can happen except discount. So if you take out the discount from 6 lakhs minus 1, 5,99,999 times. That means here we have 5,99,999 times. Other words can occur. So the combinations is 5,99,999 other words in various combinations can occur with discounts. That's going to be almost impossible to compute. Conditionality, right? This is where the assumption that discount given, if you know, we know this is a spam mail, given output is known, it's a spam or not a spam. Given this, I know if it is a spam, discount can occur. If discount occurs in the content, irrespective of other words along with the discounts, can fairly assume it looks like a spam mail. That means, given Y, probability of discounts is independent of these words. Even though we are making an assumption, it is like independent because of this observation. Even though there is a dependency, discounts can happen. For example, you received a email from GPREC saying that, hello student, you have performed in the last semester 9.99, hence GPREC is happy to announce a reduction, a discount to your tuition fee of 50%. It's a genuine email, it's not a spam, right? So that is the critical assumption, that is the naive assumption, though it works perfectly well most of the time. That is the fulcrum of naive Bayes assumption and naive Bayes model. And the power comes with it, and the ease that comes with this assumption is that because we are treating them as independent, each feature, each event, then it becomes a simple multiplication of each independent feature's probability. So it's a conditional independence, and this comes from the probability axiom we've seen, right? Probability of V2 given V1 is, we saw the Bayes rule, right? So hence we can write this, that probability of input vector being V given output, here in this case it's a scalar, being U could be either 0, not spam, or genuine, is equals to, you know this symbol, right? It's the sigma multiplication. It's a converse of sigma for multiplication. Sigma is for addition, and this pi is for multiplication, iterative multiplication of all independent, conditional independent or independent probabilities of all n samples, in this case 6 lakhs, right? Of probability of each word being Vj, or each value, each feature, occurrence of that feature given Y equals to 1. That is naive Bayes, naive assumption, and that is a naive Bayes theorem. So that is essentially, I'm going to probably not focus much on it. I have derived the principles here, but let's just look at the simple fundamentals. So if you have, in terms of training and mathematical model, if you have m samples, right, of training, the prior probability, or in general frequentist probability of jth word occurring in spam, meaning Y is 1, is nothing but simple, right? All spam emails in the training set, and which are the spam emails that contain this jth word. In our case, let's say discount. So prior probability of discount being spam, or a spam mail containing discount, prior probability would be all spam mails that are marked as spam, and out of all those, in some of them spam mails, discount word may not be there, right? Hence, so count all those mails, spam mails that have the discount in it, and put that number, and this is mathematically indicated this way. This is called indicator function. You know, indicator 1, value is 1 if xj is 1 and yi equals to it's a spam mail, 1. Otherwise, it will be 0. So that means it simply counts whether that item is there or not in the spam email. So we are counting whether the jth word, jth index value is 1. If it is 1, it is 1. And when this email is a spam, and if so, if both are true, then take the value 1. If not, if either of them is not true, the value is 0. And then you sum them up across all training samples. And here we are counting all the spam emails in the training set. This is indicator function. In the same way, a spam, prior probability of jth word not occurring in spam is straightforward. If there are only 2 events, 2 mutually exclusive events, let's say probability of A, 2 events, probability of B. There are 2 events and 2 probabilities. Probability of A plus probability of B has to be how much? Anyone? It is always 1. So probability of A equals to 1 minus probability of B. And that is what we have derived here. When we know probability of word occurring in a spam mail, when we deduct that from 1, then we get the probability of that word not occurring in the spam email. Same way, deriving the probabilities of the word in genuine email. So let's look at this again. Probability of jth word being part of a genuine email, y is 0. Obviously, we need all the emails that are genuine, which is we are counting when yi is 0, counting 1, and all those genuine emails in which jth word exists. So all the emails that are genuine, and in that the jth word is, its value is 1, it's present, then sum them up. Jth word not occurring in genuine email, that is 1 minus of occurring in genuine email. Right. Prior probability of an email being spam, simple. You know all the spam emails from the training because you've already marked them. So let's say there are 1,000 out of 6 lakh total email in your training set. So probability is 3 gone into 100. So probability is 1 by 6% of jth word being in spam or in spam email, and jth word being genuine, 1 minus being spam. So we've clearly understood prior probabilities so far. Let's understand posterior probabilities. So applying the base rule, we've derived the base rule a little while ago. So probability of output being 1, y being 1, or mail being spam, given an input email, v or v bar features is nothing but probability of given email being probability of given email being spam multiplied by our prior beliefs of spam probability divided by the probability of the likelihood, right? Beside the prior probability of the given email being spam, unconditional, right? Being genuine would be, it just changes to being genuine. Y is 0. Y is 0. This is same. So this is posterior probability, likelihood, prior probability, and evidence. Right? Questions? So we can classify an email is a spam if the posterior probability of email being spam is higher than posterior probability of email being genuine. Otherwise, it is a genuine. And if we put those formulae that we derived in the previous slides, so you would get a condition. So spam, here you would call it a spam, we saw this. And if you apply or substitute those values based on the Bayes theorem, so this, if it holds good, it's a spam, else it is not a spam. And just deriving a little bit those probabilities using the joint probabilities based on the conditional independence assumption, you would get this essentially the conditional probability here. Here it's, these are all joint probabilities essentially, right? At the vector level here at the index level, feature level, right? So if you take the natural logarithm for these two equations, you would arrive at this for spam and for genuine. So if you try to recap the 3 to 4 algorithms that we have learned, let me actually recap you guys in terms of what is the feature vector, training data, what's the predicted value, and what's the algorithm. For linear regression, our feature vector was a continuous value in the realm of real numbers, any n-dimensional, could be scalar, could be n-dimensional. Or inferred or predicted value is a continuous value, again in the realm of real number space, n-dimensional space. In case of logistic regression, our output inference was discrete, so it belonged, in case of binary, 0 or 1 or some categories multinomial, which is discrete, whereas the input was continuous or discrete as well, but continuous mostly. But naive Bayes, that is the power. Our email was discrete words and values 0 and 1. Our prediction also is whether spam or not, 0 or 1. So this is used when input is discrete, training contains discrete values, and prediction is discrete as well. When your input is discrete, when your output is continuous, we have seen it's a linear regression. But because you have input values that are discrete, you have to translate them or encode them one value to some other value. If your category, each category, multiple category values are there, then each category value has to be encoded into a different continuous value. It's called one-hot encoding, right? So the algorithms are essentially regressors with hot encoding. So naive Bayes, simple, powerful, works well when there is a relative independence or essentially the input features like discount happening mostly only in the spam filter, perfectly works. But if a discount happens also equally same amount of times in the genuine mails, we're going to fail. So weak correlation between the input vectors is a pattern that we need for this algorithm to work, to have the better accuracy. Obviously, it fails when there is a strong correlation or dependency is higher, right? Some of the cases, document classification, image recognition, speech recognition, image recognition, the background is not just 1 pixel, the part of the area 10-20%, so there is a correlation. So naive Bayes can fail. So I want you to observe one thing, it is possible that if discount was not at all there in our training, but we find a male with discount during the prediction. So what would be the value prior probability of discount? Because we did not have it, it would be 0. And since it's the joint probability multiplying other probabilities, entire joint probability, both for 1 or 0, any class, it would be 0. Right? It's actually a genuine problem. And this is called zero frequency problem. And this would be a problem for us as well, discount. So what happens if you've seen an unforeseen data during the prediction, because we don't have any prior belief or prior knowledge about it, right? So because probability becomes 0, posterior probability, because of the multiplication. This is solved using something known as Laplace smoothing or additive smoothing. As the name says, it is going to add something to ensure prior probability would not become 0 for unforeseen word, which is discount in this case. How does it achieve or accomplish? We've seen this formula. It simply adds 1 in the numerator and 2 in the denominator. And what is the significance of it? But before significance, let's see. Let's say the probability this is 0, right? Or this is 0. Then you have at least 1/2. So your posterior probability or joint probability, be it for class 1 or class 0, is not going to become a 0. Right? So the significance of this or adding the smoothing is nothing but it's like what we call it salt in case of encryption. What we call it even in the medicines that are made to make edible, lots of suspicions and then some white powders are added. It's a similar case here. Right? The significance or intuition of this addition of 1 and 2 here is that it is equivalent of adding 2 spam emails to the training set, 1 containing the word, all words in the dictionary, 1 blank, and also adding 2 genuine emails to the training set, same, 1 containing all words in the dictionary, 1 blank. 1 blank email, which is spam, 1 blank email, which is 0 zeros or spam and genuine. Right. So accuracy, precision, you all know. I'm going to skip this and we'll spend some time tomorrow. Now the project classifier, the project using Naïve Bayes. So,
sir, excuse me, sir. Sorry to interrupt.
Right.
Sir, is there any possibility to continue this in next session, sir?
Right. Well,
because in the afternoon session they're having exams, sir.
Okay, fine.
So sorry to interrupt, sir.
No problem. We
Yes,
will
sir.
wrap it up in next 1 minute.
Yes, sir.
And we will continue tomorrow.
Yes, sir. Thank you, sir. Thank you so much.
Right. So the project is the email spam filter. This is based on a very popular Apache spam assassin project. The data set is actually true emails. It would be actually pretty interesting that you would be analyzing the true emails using your code. Pretty straightforward, simple. We will go through this tomorrow, and we will also look at the code tomorrow at 10:30 tomorrow. Right, Professor?
sir. Yes, sir. 10:30, sir.
Nice. Okay. Thank you, guys, and wish you all the very best. Bye bye.
Thank you so much, sir. Yeah, sir. Nice.
Thank you. Bye bye.